How did humans acquire the power to transform the planet like this? Looking at the Earth at night reveals to us just how successful we've been in harnessing and manipulating energy and how important it is to our existence. Energy is vital to us all. We use it to build the structures that surround and protect us. We use it to power our transport and light our homes. And even more crucially, energy is essential for life itself. Without the energy we get from the food we eat, we die. But what exactly is energy, and what makes it so useful to us? In attempting to answer these questions, scientists would come up with a strange set of laws that would link together everything from engines to humans to stars. It turns out that energy, so crucial to our daily lives, also helps us make sense of the entire universe. This film is the intriguing story of how we discovered the rules that drive the universe. It's the story of how we realized that all forms of energy are destined to degrade and fall apart. To move from order to disorder. It's the story of how this amazing process has been harnessed by the universe to create everything that we see around us. Over the course of human history, we've come up with all sorts of different ways of extracting energy from our environment. Everything from picking fruit, to burning wood, to sailing boats, to water wheels. But around 300 years ago, something incredible happened. Humans developed machines that were capable of processing extraordinary amounts of energy to carry out previously unimaginable tasks. Now, this happened thanks to many people and for many different reasons, but I'd like to begin this story with one of the most intriguing characters in the history of science, one of the first to attempt to understand energy. Gottfried Leibniz was a diplomat, scientist, philosopher, and genius. He was forever trying to understand the mechanisms that made the universe work.
Leibniz, like several of his great contemporaries, was absolutely convinced that the world we see around us is a vast machine designed by a powerful and wise person. And if you could understand how machines worked, you could therefore understand how the universe and the principles that had been used to make the universe worked as well. And so there was an extremely close relationship for Leibniz between theology and philosophy on the one hand and engineering and mechanics on the other.
It was this relationship between philosophy and engineering that in 1676 would lead him to investigate what at first sight seemed to be a very simple question. What happens when objects collide? This is what Leibniz and many of his contemporaries were grappling with. So when these two balls bump into each other, the movement of one gets transferred to the other. It's as though something's being passed between them. And this is what Leibniz called the living force. He thought of it as stuff, as a real physical substance that gets exchanged during collisions.
Leibniz argued that the world is a living machine, and that inside the machine there is a quantity of living force put there by God at the creation that will stay the same forever. So the amount of living force in the world will be conserved. The puzzle was to define it.
Leibniz would soon find a simple mathematical way to describe the living force. But he would also see something else. He realized that in gunpowder, fire, and steam, his living force was being released in violent and powerful ways. If this could be harnessed, it could give humankind unimaginable power. Leibniz would soon become fascinated with ways of capturing the living force. A prolific letter writer, Leibniz struck up correspondence with a young French scientist called Denis Papin. As they corresponded, Leibniz and Papin realized the living force released in certain situations could indeed be harnessed. Heat could be converted into some form of useful action. But how far could this idea be taken? Papin was in no doubt. This is an extract from his letter to Leibniz. I can assure you that the more I go forward, the more I find reason to think highly of this invention, which in theory may augment the powers of man to infinity. But in practice, I believe I can say without exaggeration that one man by this means will be able to do as much as 100 others can do without it. Now, you might expect me at this point to tell you that Leibniz and Papin changed the world forever. Well, they hadn't. Their ideas had been profound and far-reaching, yes, but they hadn't really moved things forward. For that, you need something much more tangible. You need innovation, industry. You need countless skilled workers and craftsmen who are going to apply these ideas, to experiment with them in novel and new ways. Well, in the century that followed Leibniz and Papin, this would take place in the most dramatic way imaginable. 150 years after Leibniz and Papin's discussions, the living force had been harnessed in spectacular ways. The machines they dreamed of had become a reality. Steam engines were now the cutting edge of 19th century technology.
If you look at steps in civilization, then one great step was the steam engine, because it replaced muscle, animal muscle, including our muscle, by steam power. And the steam power was effectively limitless and hugely important to doing almost unimaginable things.
But steam technology would do more than just transform human society. It would uncover the truth about what Leibniz had called the living force and reveal new insights about the workings of our universe. This is Cross Ness in southeast London. It's an incredible industrial cathedral and home to some of the most impressive Victorian steam engines ever built. Constructed in 1854, Cross Ness houses 4 huge engines that once required 5,000 tons of coal each year to drive their 47-ton beams. Everything about this place seems to have been built to impress. From the lavish ironwork, the grand pillars like something out of a Greek or Roman temple. It's the sort of effort you'd think would have been lavished on a luxury ocean liner for the rich and famous. And yet this place was built to process sewage. Although only a few workers and engineers would have seen the insides of this place, steam had become such a vital part of British power and economic prosperity that it was afforded almost religious respect. But for all the great success and immense power that engines were bestowing on their creators, there was still a great deal of confusion and mystery surrounding exactly how and why they worked. In particular, questions like how efficient could they be made? Were there limits to their power? Ultimately, people wanted to know just what might it be possible to achieve with steam. The reason these questions persisted was simple. Almost no one had understood the fundamental nature of the steam engine. Very few were aware of the cosmic principle which underpinned it.
These great lumbering machines that we think of as the early steam engines actually were the seed of understanding of everything that goes on in the universe.
As unlikely as it sounds, steam engines held within them the secrets of the cosmos. This is the Château de Vincennes in Paris. Events here would motivate one man's journey to uncover the cosmic truth about the steam engine and help to create a new science, the science of heat and motion, thermodynamics. In March 1814, during the Napoleonic Wars, when Napoleon and his armies were fighting elsewhere, Paris itself came under sustained attack from the combined forces of Russia, Prussia, and Austria. And citizens of the city were deployed around key locations to protect them. Now, this chateau was being defended by a group of inexperienced young students who were forced to retreat under sustained artillery fire. One of them was a brilliant young scientist and soldier. His name was Nicolas Léonard Sadi Carnot, and the humiliation he felt personally would drive him and motivate him to uncover a profound insight into how all engines work. Carnot came from a highly respected military family. After the French defeat here and elsewhere around Europe, he became determined to reclaim French pride. What really bothered Carnot was the technological superiority that France's enemies seemed to possess. And Britain in particular had this huge advantage, both militarily and economically, because of its mastery of steam power. So Carnot vowed to really try and understand how steam engines work and use that knowledge for the benefit of France.
He says absolutely explicitly that if you could take away steam engines from Britain, then the British Empire would collapse. And he's writing in the wake of French military defeat, and he proposes to analyse, literally, the source of British power by analysing the way in which fire and heat engines work.
Living on half pay with his brother Hippolyte in a small apartment in Paris, in 1824, Carnot wrote the now legendary Reflections on the Motive Power of Fire. In just under 60 pages, he developed and abstracted the fundamental way in which all heat engines work. Carnot saw that all heat engines comprised of a hot source in cooler surroundings. Now, Carnot believed that heat was some kind of substance that would flow like water from the hot to the cool. And just like water falling from a height, the flow of heat could be tapped to do useful work. Carnot's crucial insight was to show that to make any heat engine more efficient, all you had to do was to increase the difference in temperature between the heat source and the cooler surroundings. This idea has guided engineers for 200 years. Ultimately, a car engine is more efficient than a steam engine because it runs at a much hotter temperature. Jet engines are more efficient still, thanks to the incredible temperatures they can run at. Carnot had revealed that heat engines weren't just a clever invention. They were tapping into a deeper property of nature. They were exploiting the flow of energy between hot and cold. Carnot had glimpsed the true nature of heat engines, and in the process begun a new branch of science. But he would never see the impact his idea would have on the world. In 1832, a cholera epidemic spread through Paris. It was so severe it would kill almost 19,000 people. Now, back then there was no real scientific understanding of how the disease spread, so it must have been terrifying. Carnot, undaunted by the risks, decided to study and document the spread of the disease. But unfortunately, he contracted it himself and was dead a day later. He was just 36 years old. A lot of his precious scientific papers were burnt to stop the spread of contagion, and his ideas fell into temporary obscurity. It seems the world wasn't quite ready for Carnot. Carnot had made the first great contribution to the science of thermodynamics. But as the 19th century progressed, the study of heat, motion, and energy began to grip the wider scientific community. Soon, it was realized that these ideas could do much more than simply explain how heat engines worked. Just as Leibniz had suspected with his notion of living force, these ideas were applicable on a much grander scale. By the mid-19th century, scientists and engineers had worked out very precisely how different forms of energy relate to each other. They measured how much of a particular kind of energy is needed to make a certain amount of a different kind. Let me give you an example. The amount of energy needed to heat 30 millilitres of water by 1 degree centigrade is the same as the amount of energy needed to lift this 12.5 kilogram weight by 1 metre. The deeper point here that people realised was that although mechanical work and heat may seem very different, they are in fact both facets of the same thing: energy.
This idea would come to be known as the first law of thermodynamics. The first law reveals that energy is never created or destroyed. It just changes from one form to another. 19th century scientists realized this meant the total energy of the entire universe is actually fixed. Amazingly, there's a set amount of energy that just changes into many different forms. So, in a steam engine, energy isn't created. It's just changed from heat into mechanical work.
But impressive though the first law is, it begged an enormous question. What exactly is going on when one form of energy changes into another? In fact, why does it do it at all?
The answer would in part be found by German scientist Rudolf Clausius, and it would form the basis of what would become known as the second law of thermodynamics.
Rudolf Clausius was a brilliant German physics student from Pomerania who studied in Berlin and at a ridiculously young age became a very brilliant professor in Berlin and then in Zurich at the new technology university set up there in Switzerland. And in the 1850s and 60s, Clausius offered what is really the first coherent, full-blown mathematical analysis of how thermodynamics works.
Clausius realized that not only was there a fixed amount of energy in the universe, but that the energy seemed to be following a very strict rule. Put simply, energy in the form of heat always moved in one particular direction.
This insight of his is in fact one of the most important ideas in the whole of science. As Clausius put it, heat cannot of itself pass from a colder to a hotter body. This is a very intuitive idea. If left alone, this hot mug of tea will always cool down. What this means is that heat will pass from the hot mug, say, to my hand, and then again from my hand to my chest.
This might seem completely obvious, but it was a crucial insight. The flow of heat was a one-way process that seemed to be built very fundamentally into the workings of the entire universe. Of course, objects can get hotter, but you always need to do something to them to make this happen. Left alone, energy seems to always go from being concentrated to being dispersed.
One of my favourite statements in science was made by the biochemist Albert St. George, who said that science is all about seeing what everyone else has seen, but thinking what no one else has thought. And he, Rudolf Clausius, looked at the everyday world and saw what everyone else had seen, that heat does not flow spontaneously from a cold body to a hot body. It always goes the other way. But he didn't just say, I see that. He actually sat down and thought about it.
Clausius brought together all these ideas about how energy is transferred and put them into mathematical context. It could be summarized by this equation. Now, what Clausius did was introduce a new quantity he called entropy, this letter S. Basically, what it's saying in the context of this equation is that as heat is transferred from hotter to colder bodies, entropy always increases.
Entropy seemed to be a measure of how heat dissipates or spreads out. As hot things cool, their entropy increases. It appeared to Clausius that in any isolated system, this process would be irreversible.
Clausius was so confident about his mathematics that he figured out that this irreversible process was going on out there in the wider cosmos. He speculated that the entropy of the entire universe had to be increasing towards a maximum, and that there was nothing we could do to avoid this. This idea became known as the second law of thermodynamics, and it turned out to be stranger and more beautiful, more universal than anything Clausius could have imagined.
The second law of thermodynamics seemed to say that all things that gave off heat were in some way connected together. All things that gave off heat were part of an irreversible process that was happening everywhere. A process of spreading out and dispersing. A process of increasing entropy. It seemed that somehow the universe shared the same fate as a cup of tea.
The wonderful thing about the Victorian scientists is that they could make these great leaps, and that they could see that their study of a thermometer in a beaker actually could be extrapolated, could be enlarged to encompass the whole universe.
Despite the successes of thermodynamics, in the middle of the 19th century, there was great debate and confusion about the subject. What exactly was this strange thing called entropy? And why was it always increasing? Answering this question would take an incredible intellectual leap, but it would end up revealing the truth about energy and the many forms of order and disorder we see in the universe around us.
Many scientists would tackle the mysterious concept of entropy, but one more than any other would shed light on the truth. He'd show what entropy really was and why, over time, it always must increase. His name was Ludwig Boltzmann, and he was one of science's true revolutionaries.
Boltzmann had been born in Vienna in 1844. It was a world of scientific and cultural certainty. But Boltzmann took little notice of the entrenched beliefs of his contemporaries. To him, the physical world was something best explored with an open mind.
Boltzmann wasn't your stereotypical scientist. In fact, he had the kind of temperament that most people might associate with great artists. He was ruthlessly logical and analytical, yes, but while working, he'd go through periods of intense emotion, and these would be followed by terrible depressions, which would leave him completely unable to think clearly.
He had terrible sort of mental crises and breakdowns in which he really thought that the world was coming apart at the seams. And yet, these were also accompanied by some of the most profound insights into the nature of our world.
Outside of mathematics, Boltzmann was passionate about music and was captivated by the grand and dramatic operas of Wagner and the raw emotion of Beethoven. He was a brilliant pianist and could lose himself for hours in the works of his favorite composers, just as he could lose himself in deep mathematical theories.
Boltzmann was a scientist guided by his emotions and instinct, and also by his belief in the ability of mathematics to unlock the secrets of nature. It was these traits that would lead him to become one of the champions of a shocking and controversial new theory, one that would describe reality at the very smallest scales, far smaller than anything we could see with the naked eye.
During the second half of the 19th century, a small group of scientists began speculating that at the smallest scales, the universe might operate very differently to our everyday experiences. If you could look close enough, it seemed possible that the universe might be made of tiny, hard particles in constant motion. Viewed in terms of atoms, heat would suddenly become a much less mysterious concept. Boltzmann and others saw that if an object was hot, it simply meant that its atoms were moving about more rapidly. Viewing the world as atoms seemed to be an immensely powerful idea. But this picture of the universe had one seemingly insurmountable problem.
How could trillions and trillions of atoms, even in a tiny volume of gas, ever be studied? How could we come up with mathematical equations to describe all of this? After all, atoms are constantly bumping into each other, changing direction, changing speed, and there are just so many of them. It seemed almost an impossible problem. But then Boltzmann saw there was a way.
Boltzmann saw more clearly than anyone that for physics to explain this new strata of reality, it had to abandon certainty. Instead of trying to understand and measure the exact movements of each individual atom, Boltzmann saw you could build working theories simply by using the probability that atoms would be traveling at certain speeds and in certain directions. Boltzmann had transported himself inside matter. He'd imagined a world beneath our everyday reality and found a mathematics to describe it. It would be here, at this scale, that Boltzmann would one day manage to unlock energy's deepest secret, despite the widespread hostility to his theories.
Boltzmann's ideas were highly, highly controversial. And you have to remember that, today we take atoms for granted. But the reason we take atoms for granted is precisely because Boltzmann's mathematics married up so beautifully with experiment.
One of the most surprising aspects of this story is that many of Boltzmann's contemporaries viewed his ideas about atoms with intense hostility. Today, the existence of atoms, the idea that all matter is composed of tiny particles, is something we accept without question. But back in Boltzmann's time, there were notable, eminent physicists who just didn't buy it. Why would they? No one had ever seen an atom, and probably no one ever would. How could these particles be considered as real? After one of Boltzmann's lectures of atomic theory in Vienna, the great Austrian physicist Ernst Mach stood up and said simply, "I don't believe that atoms exist." It was both cutting and dismissive. And for such a comment to come from a highly regarded scientist like Ernst Mach, it would have been doubly hurtful.
They argued that no, atoms don't exist. They're names, labels, convenient fictions, calculating devices. They don't really exist. We can't observe them. No one's ever seen one. And for that reason, so Boltzmann's critics said, he was a fantasist.
But Boltzmann was right. He peered deeper into reality than anyone else had dared, and seen that the universe could be built from the atomic hypothesis and understood through the mathematics of probability. The foundations and certainty of 19th century science were beginning to crumble.
As Boltzmann stared into his brave new world of atoms, he began to realize his new vision of the universe contained within it an explanation to one of the biggest mysteries in science. Boltzmann saw that atoms could reveal why the second law of thermodynamics was true, why nature was engaged in an irreversible process. Atoms had the power to reveal what entropy really was, and why it must always increase.
Boltzmann understood that all objects, these walls, you, me, the air in this room, are made up of much tinier constituents. Basically, everything we see is an assembly of trillions and trillions of atoms and molecules. And this was the key to his insight about entropy and the second law.
Boltzmann saw what Clausius could not. The real reason why a hot object left alone will always cool down. Imagine a lump of hot metal. The atoms inside it are jostling around. But as they jostle, the atoms at the edge of the object transfer some of their energy to the atoms in the surface of the table. These atoms then bump into their neighbors, and in this way, the heat energy slowly and very naturally spreads out and disperses. The whole system has gone from being in a very special, ordered state, with all the energy concentrated in one place, to a disordered state, where the same amount of energy is now distributed among many more atoms. Boltzmann's brilliant mind saw this whole process could be described mathematically.
Boltzmann's great contribution was that although we can talk in rather sort of casual terms about things getting worse and disorder increases. The great contribution of Boltzmann is that he could put numbers to it. And so he was able to derive a formula which enabled you to calculate the disorder of a system.
This is Boltzmann's famous equation. It will be his enduring contribution to science. So much so, it was engraved on his tombstone in Vienna. What this equation means in essence is that there are many more ways for things to be messy and disordered than there are for them to be tidy and ordered. That's why, left to itself, the universe will always get messier. Things will move from order to disorder. It's a law that applies to everything, from a dropped jug to a burning star, a hot cup of tea to the products that we consume every day. All of this is an expression of the universe's tendency to move from order to disorder. Disorder is the fate of everything. Clausius had shown that something he called entropy was getting bigger all the time. Now Boltzmann had revealed what this really meant. Entropy was in fact a measure of the disorder of things.
Energy is crumbling away. It's crumbling away now as we speak. So the second law is all about entropy increasing, which is just a technical way of saying that things get worse.
Boltzmann's passionate and romantic sensibility and his belief in the power of mathematics had led him to one of the most important discoveries in the history of science. But those very same intense emotions had a dark and ultimately self-destructive side.
Throughout his life, Boltzmann had been prone to severe bouts of depression. Sometimes these were induced by the criticisms of his theories, and sometimes they just happened. In 1906, he was forced to take a break from his studies in Vienna during a particularly bad episode.
In September 1906, Boltzmann and his family were on holiday in Duino, near Trieste in Italy. While his wife and family were out at the beach, Boltzmann hanged himself, bringing his short time in our universe to an abrupt end. But perhaps the saddest aspect of Boltzmann's story is that within just a few years of his death, his ideas that had been attacked and ridiculed during his lifetime were finally accepted. What's more, they became the new scientific orthodoxy.
In the end, there is no escaping entropy. It's the ultimate move from order to decay and disorder that rules us all. Boltzmann's equation contains within it the mortality of everything from a china jug to a human life to the universe itself. The process of change and degradation is unavoidable. The second law says the universe itself must one day reach a point of maximum entropy, maximum disorder. The universe itself must one day die. If everything degrades, if everything becomes disordered, you might be wondering how it is that we exist. How exactly did the universe manage to create the exquisite complexity and structure of life on Earth? Contrary to what you might think, it's precisely because of the second law that all this exists. The great disordering of the cosmos gives rise to its complexity.
It's possible to harness this natural flow from order to disorder, to tap into the process and generate something new, to create new order, new structure. It's what the early steam pioneers had unwittingly hit upon with their engines. And it's what makes everything we deem special in our world, from this car, to buildings, to works of art, even to life itself. The engine of my car, like all engines, is designed to exploit the second law. It starts out with something nice and ordered, like this petrol, stuffed full of energy. But when it's ignited in the engine, it turns this compact liquid into a mixture of gases 2,000 times greater in volume, not to mention dumping heat and sound into the environment. It's turning order into disorder. What's so spectacularly clever about my car is that it can harness that dissipating energy. It can siphon off a small bit of it and use it for a more ordered process, like driving the pistons which turn the wheels. That's what engines do. They tap into that flow from order to disorder and do something useful. But it's not just cars. Evolution has designed our bodies to work thanks to the very same principle. If I eat this chocolate bar packed full of nice, ordered energy, my body processes it and turns it into more disordered energy, but powers itself off the proceeds.
Both cars and humans power themselves by tapping into the great cosmic flow from order to disorder.
Although overall the world is falling apart in disorder, it's doing it in a seriously interesting way. It's like a waterfall that is rushing down, but the waterfall throws up a spray of structure, and that spray of structure might be you or me or a daffodil or whatever. So you can see that the unwinding of the universe, this collapse into disorder, can in fact be constructive.
Steam engines, power stations, life on Earth. All of these things harness the cosmic flow from order to disorder. The reason the Earth now looks the way it does is because we've learnt to harness the disintegrating energy of the universe to maintain and improve our small pocket of order. But as humankind has evolved, we've had to find new pieces of concentrated energy we can break down to drive the ever more demanding construction of our technologies, our cities, and our society. From food to wood to fossil fuels, over human history we've discovered ever more concentrated forms of energy to unlock in order to flourish. Now, in the 21st century, we're on the cusp of harnessing the ultimate form of concentrated energy, the stuff that powers the sun: hydrogen. This is the Culham Centre for Fusion Energy in Oxford. And at this facility, they're attempting to recreate a star here on Earth. But as you might imagine, creating and containing a small star is not an easy process. It requires many hundreds of people and some extremely ingenious technology. This machine is called a tokamak, and it's designed to extract an ancient type of highly concentrated energy, the ordered energy of hydrogen atoms. These tiny packets of energy were forged in the early universe, just 3 minutes after the moment of creation itself. Now, using the tokamak, we can extract the concentrated energy contained in these atoms by fusing them together.
Inside the tokamak machine, two types of hydrogen gas, deuterium and tritium, are mixed together into a superhot state called a plasma. Now, when running, this plasma can reach the incredible temperature of 150 million degrees. Large magnets in the wall of the tokamak contain the plasma and stop it from touching the sides where it can cool down. Now, when it gets hot enough, the two types of hydrogen atoms fuse together to form helium and spit out a neutron. Now, these neutrons fly out of the plasma and hit the walls of the tokamak. But they carry energy, and the hope is that this energy can one day be used to heat up water, turn it into steam, to drive a turbine and generate electricity. Essentially, for a brief moment, inside the tokamak, a small donut-shaped star is created.
The problem is, it's extremely difficult to sustain the fusion reaction for long enough to harvest the energy from it. And that's what the scientists at Culham are working to perfect.
It's a sort of boundary between physics and engineering. How do we hold on to this very, very hot thing, which is the plasma, and how do we optimize the way the performance of this plasma? So what we really want is that the particles stay in there for as long as it's all possible to maximize their chance of hitting each other. We're trying to push this to the limit with what we have available in this machine. And whatever we can learn to understand this plasma better will also allow us to design a better machine in the future.
You can see, although it happens several times a day, oh, here we go. See, the scientists here all gather around the screens Ah, okay, it's about to come on.
What the tokamak is doing is mining the fertile ashes of the Big Bang, extracting concentrated energy captured at the beginning of time. As hydrogen is the most abundant element in the universe, if future machines can sustain fusion reactions, they offer us the possibility of almost unlimited energy. From a science that began as the byproduct of questions about steam engines, thermodynamics has had a staggering impact on all our lives. It has shown us why we must consume concentrated energy to stay alive, and has revealed to us how the universe itself is likely to end. Looking at the Earth at night reveals how one seemingly simple idea transformed the planet.
Over the past 300 years, we've developed ever more ingenious ways to harness the concentrated energy from the world around us. But all our efforts and achievements are quite insignificant when viewed from the perspective of the wider universe. As far as it's concerned, all we're doing is trying to preserve this tiny pocket of order in a cosmos that's falling apart. Although we can never escape our ultimate fate, the laws of physics have allowed us this brief, beautiful, creative moment in the great cosmic unwinding. My hope is that by understanding the universe in ever greater detail, we can stretch this moment for many millions, maybe even billions of years to come. The concept of information is a very strange one. It's actually a very difficult idea to get your head round. But in the journey to try and understand it, scientists would discover that information is actually a fundamental part of our universe.
And there's more Big Science here on BBC HD at 7 o'clock tomorrow with the science of chance in Tales You Win.